Hi everyone, Dr. Mike here. In this video, we're taking a look at how we can turn one glucose molecule into 32 ATP molecules through the process of aerobic respiration. Now, I know that sometimes it can be quite difficult to learn this in class and some teachers aren't the best at explaining it, but I think we can get this sorted pretty easily. Let's take a look. All right, so to begin, we are starting off with a cell. Now, this cell could be a muscle cell, it could be an adipose cell, it could be a liver cell. We're focusing on a liver cell here. So we've got a hepatocyte, we've got the cytoplasm here, then we've got the mitochondria here. We are going to take a look firstly at glucose. So you've just eaten a meal, your glucose levels go up in your bloodstream. So you've got a lot of glucose in your bloodstream, and you need that glucose to get from your bloodstream into this hepatocyte, and it will go through a glucose transporter. Now here's the thing, depending on the cell type, that glucose transporter might need insulin to trigger the glucose entering. In the liver, it does not require insulin. So it will simply move down its concentration gradient and get into this hepatocyte. Now we've got glucose, right? What we want to do is we need to take this glucose and we ultimately want to go through glycolysis, produce pyruvate, turn it into acetyl-CoA, allow for that acetyl-CoA in the mitochondria to enter what's called the citric acid cycle or the Krebs cycle, and ultimately feed some products off to the electron transport chain to produce 32 ATP molecules. So we want to turn one glucose molecule into 32 ATP molecules. So how does this work? All right, we've got that glucose in. We don't want it to leave. We want to trap it inside. So what we want to do is phosphorylate it. So if you take ATP, which has 3 phosphates, and give one of those phosphates off to glucose, we obviously produce ADP, but we've phosphorylated glucose. And so we've phosphorylated it at the 6th position. So this is glucose 6 phosphate. This is now trapped. Brilliant. That's why we phosphorylate it in the beginning. But it's cost us 1 ATP molecule. Then we rearrange that molecule to fructose 6 phosphate, and then we give it another phosphate. So we take another ATP molecule, hand it off one of the phosphates to produce ADP. And the reason why we do this isn't to trap it, it's already trapped. It's to make it highly energetic. We want to make it more energetic because we want to split it in half. And that's exactly what we do. We split fructose 1,6-bisphosphate into 2 glyceraldehyde 3 phosphates. This is the investment phase. In this investment phase, so let's write this up. During glycolysis, right, we have invested 2 ATP molecules so far. All right, now what we do is we've got glyceraldehyde 3 phosphate and it turns into 1,3-bisphosphoglycerate, which turns into 3-phosphoglycerate. Here, we generate some more ATP. We actually steal phosphate back. So we take ADP and we turn it into ATP. But here's the thing. Because we've got 2 of these, remember, fructose 1,6-bisphosphate, or fructose 1,6-bisphosphate, we split in half. So we've got 2 glyceraldehyde 3 phosphate, 2 1,3-bisphosphoglycerate, and so forth, right? 2, 2, 2. So that means we actually take 2 ADP and produce 2 ATP. So we've got 2 ATP here. Then we go to 3-phosphoglycerate, and then phosphoenol pyruvate, and we turn 2-phosphoenol pyruvate into 2-pyruvate, and in this process of turning phosphoenol pyruvate into pyruvate, we generate more ATP again. So we take 2 ADP and we turn it into 2 ATP. So look at that. This is glycolysis. What we've just done is we've lost 2 ATP, but we've gained 4 ATP. So now we've gained 4 ATP. So what is our net gain? We've got a net gain of 2 ATP in the process of glycolysis. So that is 2 ATP. We've got 30 left to explain. But here's the thing, right? This is why glycolysis is so good at producing energy quickly, right? It's producing energy, not a lot, but it does it very quickly. But here's the important thing, right? This is what people don't explain very well. Glucose, we started with glucose, we ended with pyruvate, right? So let's just, okay, what glucose is, and I'll write this here, right? So glucose. Glucose is made up of 6 carbons, 12 hydrogens, and 6 oxygens. C6H12O6, that's the chemical formula of glucose, right? Now, after all this to create 2-pyruvate, what is pyruvate? Pyruvate is C3H4O3. But we've got 2 of them, right? We've got 2 of them. So in actual fact, that is C6H8O6. Now compare that to that. We've still got 6 carbons, so we didn't lose any carbons in this process. We've lost 4 hydrogen, and we didn't lose any oxygen. So effectively, going from glucose to pyruvate, all we've done is generated 2 ATP and lost 4 hydrogen. Where did these 4 hydrogen go? That's really important because we need to talk about how we plucked off those 4 hydrogen. So this is where we need to talk about something called NAD+, forming NADH. So again, keep in mind, we need to find out where 4 hydrogen went. So firstly, we've got something called NAD+, nicotinamide adenine dinucleotide. It has a job, and that job is to steal hydrogen. Ooh, okay, it's stealing hydrogen. But you need to keep in mind what hydrogen is. Hydrogen is the first element on the periodic table. It's made up of 1 proton and 1 electron, right? That's it, that's what it's made. So here it's neutral, right? Now if I were to pluck off that electron, I'm simply left with the proton, H+, and that's why hydrogen ion, H+, is also just called a proton, because that's all it effectively is. What NAD+ wants to do is it wants to steal 2 hydrogen. So let's write the second hydrogen up here. So there's the second hydrogen. So NAD+ steals 2 hydrogen. But then what it does is it takes the proton and throws it away. So what it actually steals is 2 electrons and 1 proton. So it steals 2 electrons and 1 proton, and what it ends up producing is NADH, right? Because have a look, 1 positive plus 1 positive is 2 positives. So you have NADH with 2 positives, which is then neutralized by the 2 negatives. So you produce that, and what I said was you're left with 1 hydrogen ion floating in the solution. Remember, what makes an environment acidic? An accumulation of those. So in this process of NAD+ stealing hydrogens from the rearrangement of these glucose molecules, we actually make the solution acidic. Keep that in mind. That is actually important when it comes to metabolism. So the question is, where is NAD+ stealing these hydrogens from? Remember, it needs to steal 4 in order to make up for the 4 that we lost. So effectively, this is happening here. Going from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate, we are taking NAD+ and turning it into NADH. But remember, there's 2 of them. 2 there, 2 there. Now remember, NAD+ steals 2 hydrogens. 1 it keeps, 1 it throws away. And if we're doing that twice, it's stealing 4 hydrogens, right? So we could easily write it like this. 2 there, so that will end up becoming 4. That will become 2, right? And that will become 2. And that will become 2 as well, right? So we produce 2 NADH. There we go. Release 2 protons. So that's where those, now the question is, why do we need NADH stealing protons and electrons? Think of it carrying. It's carrying protons and electrons, and it's ultimately going to carry it here into the electron transport chain. So effectively, this NADH is throwing it into here. Now, what I want to do is write it down. Let's write this down here. In addition, in glycolysis, we produce 2 NADH. H. All right, great. Now what we need to talk about is entering the mitochondria. So the pyruvate that we've made, the 2-pyruvate, enter the mitochondria and turn into acetyl-CoA. Interestingly, in this process of creating acetyl-CoA, it turns, actually I wrote it in blue before, so I'll write it in blue again. It turns NAD plus into, what do you reckon? NADH. But remember, there's 2-pyruvate, so it turns 2 NAD plus into 2 NADH. Now, even though I've only written 1 acetyl-CoA, there's 2 of each of these with every cycle. Okay, so now we've produced more NADH. So let's write this down. So we've got, from the process of pyruvate, we've also produced 2 NADH. Now let's look at the Krebs cycle, which is also known as the citric acid cycle, right? Also known as the citric acid cycle and the Krebs cycle. So acetyl-CoA will bind with oxaloacetate, turn into citrate, isocitrate, alpha-ketoglutarate, succinyl-CoA, succinate, fumarate, malate, and back to oxaloacetate. All right, what's happening here? So effectively, from isocitrate to alpha-ketoglutarate, we're taking NAD plus and turning it into NADH. But remember, times 2. We'll put the times 2 in once we're done. That happens again here. NAD plus goes to NADH. Here we actually produce ATP. Effectively it's GTP, but that turns into ATP. So we'll say ADP going into ATP. Again, 2 of them will be made. Here we actually have another molecule that's very similar to NAD and NADH. It's called FAD. So we take FAD and it steals 2 hydrogens and turn into FADH, but FADH2 specifically. But again, it's just carrying hydrogens and electrons, right? And then we've got malate going to oxaloacetate, NAD plus going to NADH. Now let's put the times 2 in, because that's important. So in the Krebs cycle, we produce 2, 4, 6 NAD plus, right? So we produced 6 NADH, sorry, not NAD plus. 6 NADH, right? We produced 2 ATP. We produced 2 FADH. FADH2 to be specific. All right. So far, how many ATP have we made? We've made, so we can ignore this, right? Because that was just to do the maths. So this was the product. We've created 2 ATP, 4 ATP. Okay, we've created 4 ATP. It's a long way off 32, but we've created NADH, 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 FADH2. They're carrying hydrogens and electrons to the electron transport chain. So think about it like this. What we end up having, I'll draw it like this. We've got FADH2 and NADH. And they say, okay, I've carried all my electrons and protons here, so it dumps off hydrogen ions and it dumps off electrons, because that's what it stole, right? And that's what it was carrying. Now so it's gone blunk, dumps it off. So FADH turns back into FAD, NADH turns back into NAD+, can be reused again. Brilliant. Now what happens is this. The electrons will jump from these, so remember the mitochondria has an outside mitochondrial membrane and an internal mitochondrial membrane and an intermembrane space. An outer and an inner mitochondrial membrane. Embedded in the inner mitochondrial membrane are these proteins. Some work as pumps, some don't. Here, electrons are passed from pump to pump, right? And what it does is it excites them, to go, whoa, I'm excited now. I'm going to pump hydrogens into this intermembrane space. I'm going to pump hydrogens into this intermembrane space because it's all excited to do that. So now that we've accumulated all these hydrogens into this intermembrane space, they've got a concentration gradient, and they go down their concentration gradient through this last channel here. And what this is it's called an ATP synthase. It makes ATP because as the hydrogen moves down, it spins that turbine. It piggybacks on the energy of the hydrogen moving down, spins that turbine to produce ATP. So effectively, FADH2 and NADH, by dumping off hydrogens and electrons, will produce ATP through this process. How many ATP do they produce? Well, one NADH will produce 2.5 ATP. One FADH2 will produce 1.5 ATP. So all we need to do here is our maths, right? So we've got, let's add up, no, let's do it like this. So multiply that by 2.5, multiply that by 2.5, multiply that by 2.5, multiply that by 1.5. What do we have? Okay, so 2 times 2.5 is 5. 2 times 2.5 is 5. 6 times 2.5, that's going to be 12, 30, 40, 15. And then 2 times 1.5 is going to be 3 ATP. So how many ATP have we made? 2 plus 5 is 7, plus another 5 is going to be 12, plus 15 is 27, 28, 29, 30, 31, 32. We've just produced our 32 ATP molecules. Isn't that beautiful? Now, just to finalize this point, what happens with the hydrogens and the electrons? Because once the electrons have hit their final protein, now, the electrons, remember, when you lose an electron, that's called oxidation. When you gain an electron, it's called reduction. So these proteins are getting reduced. And once they're reduced, they can't become any more reduced. So once an electron's been given to, these are called cytochromes, right? They're the things that become reduced. They can't accept any more cytochrome. They can't accept any more electrons, right? So this will back up. So we need somewhere to put the last electron. Otherwise, the whole thing backs up. So what we end up getting is oxygen. Right? We take oxygen. So remember, we've got oxygen, which we breathe in, hence why it's called aerobic respiration. And that oxygen will take on board electrons, and it will take on board protons. Now, if you take on electrons and protons and mix it together, if we take on, let's say, 4 negative electrons and 4 positive protons, with 2 oxygens, what do you think we end up producing? 2 H2O. We produce 2 water molecules. So for every oxygen gas we breathe in, it will say, hey, don't worry, I'll be the ultimate electron or terminal electron acceptor, and I'll take the proton. So those things, so protons, they're damaging, don't worry, I'll take it. The electrons, they're damaging, I'll take it, and I'll just turn into innocuous water, something that doesn't harm the body and can move through the body beautifully. Now, this is why it's called aerobic respiration. This is so important. Without enough oxygen to take the protons and the electrons from the electron transport chain, the electrons will back up. And if they back up, the protons won't get pumped. If they don't get pumped, the NADH and FADH will be holding on to them. And if they hold on to them, they don't regenerate their NAD plus and FAD, which means citric acid cycle backs up. And the whole thing backs up. And so what ends up happening is we don't do aerobic respiration. We have to do anaerobic respiration, which effectively is this, because what happens here is we go from glucose to pyruvate, but pyruvate can't enter this process, so pyruvate turns into lactate. And that's anaerobic respiration. That's for another video. I'm Dr. Mike, and I hope that helps. Hi everyone, Dr. Mike here. If you enjoyed this video, please hit like and subscribe. We've got hundreds of others just like this. If you want to contact us, please do so on social media. We are on Instagram, Twitter, and TikTok at Dr. Mike Todorovic, at DrMikeTodorovic. Speak to you soon.